Okay, good morning, everyone. Welcome to this talk. It's so good to see so many of you here. My name's Hanno, and I always love speaking at jfall because it's my home conference, right? I think to a lot of you, it's your home conference, and I always enjoy these dates tremendously. And I'm looking forward to talk with you today about concurrency in Java. Now, many of you may know concurrency has had a long journey in the past in Java, right? And started in the late 90s. And Java's support for concurrency has certainly improved massively over time. And in this talk, I want to focus on the latest additions, so the introduction of virtual threads and everything that comes after that came out of Project Loom. And when you deal with a complicated topic, it's always my preference to pick a very simple example domain so that we can focus on the complicated topic instead of everything around it. And the domain I want to introduce to you today is the bar and restaurant domain, and there's a very particular reason for that. It's because I got the idea for this talk while I was at a bar. So at InfoSupport, we have a Java community, and we had a nice dinner, and before the dinner, we had some drinks, and we were at this bar and restaurant, and the waiter came up to us and said, hi, good evening, what can I get you people to drink? And we were like, what do you have in stock? And he started listing these drinks, right? So he just created an entirely long sentence, didn't give us a menu or something, just said, well, we have some beers, and he started listing various brands of beer. We have some wines, you can get a coffee, you can get a soft drink. And we were kind of uneasy. We were feeling uneasy because we thought, this poor guy is listing the entire menu, right? And we already know what we want. But we're just polite, so we're letting him finish this giant sentence. So he was done. He listed like 25 different drinks. And I said, yeah, what was the first one again, right? He was so frustrated. He says, couldn't you have told me? And that's when I thought, wow, the new structured concurrency features in Java would be perfect to solve this scenario, right? There's a successful result, stop everything else, and return the result to me. I'm not sure what that says about me, right? It's a Friday evening, I can unwind, relax, and I'm still thinking about Java. I mean, it's probably is my entire life, and not just my work. But I'm not ashamed of that, right? To get to virtual threads and structured concurrency and scoped values, I feel I owe you kind of an introduction, but I'll try to keep it short. So this bar, this restaurant, that we are taking as an example today is kind of modeled after this. Who is a Sesame Street fan or watched it when they were younger? I was a massive Sesame Street fan. It was in the age before Netflix, right? My kids don't know what's fun about it because they were like, nothing happens, right? Where's all the noise and the stuff happening? Generational differences, I guess. By the way, my wife is excellent at drawing, so she drew this up for me. So I'm really grateful for that. The relationship works because we are opposites, right? I cannot draw anything for my life, and she does this, so in like 20 minutes. And it helped me, steer clear of some copyright infringements, right? So that's also a bonus. We are going to model a restaurant, and if you're a Sesame Street fan or watched it when you were young, you know that in the Sesame Street restaurant, a lot of things go wrong. The waiter Grover is kind of clumsy and always delivers the stuff that wasn't ordered, so like a Lego brick instead of a nice meal. If we would model a restaurant in Java with threads, right, the basic building block of concurrency in Java, we would then introduce an interface called restaurant with a single method announce menu. So this is the method that we are going to implement with various ways to do structured concurrency or unstructured concurrency, as we will see. This is probably what you would do if you would just use threads from the Java 1.0 version, right? Create 3 waiters, create 3 threads. Those are then subclasses of the Java thread class. You have to start them. Where is my pointer? It's here. Start them. You have to join all of them to make sure that at the end everything is done, and then you can announce the courses. This was before callables, right? In Java 5.0, we got the callables. That meant that we could just define a task and get a result out of it. But in the Java 1.0 era, we had to, put a field in the subclass of thread, something like this, right? And then this announced course here would then be filled up, and then the result will be available. Pros and cons time. Well, threads obviously allow us to do multiple things at once, but we can't return a value directly, at least not with the first version of Java. We had to create a field for that. And also, when you create a thread, the workload, so what you want the thread to do, and the mechanism to run it, they are very closely linked, right? We are defining both what to do, and you should run it on this particular thread. So there's a very tight coupling there. And that's not really working for us. What if I wanted to increase to 6 threads or 9 threads or just a single one? We would have to remodel it all over again with lots of work. So if we would introduce executor service, which came to us in Java 5, along with callables, then our code example would change and it would become something like this. And in this case, we are using 3 threads, but we're actually initializing the executor service here with 3 threads. We could also use 5 or 8 or a single one, or use thread caching if we wanted to. And in this case, we are submitting 3 announce course invocations, and this time we get futures out of them. Well, futures are great, except when you have to call get on them, and that's mostly what we do in the end. Here we call get on the futures, and as you may know, get is a blocking method, which means the thread that is running it will be suspended until the result is available. So there's no way for us to define here what happens if one of the gets fails or something, or if we want to do something else after that. Okay, and this is all fine and dandy, I think, this implementation here, because we improved on the solution before. But what if we would introduce an element of surprise into this code? So, for example, let's assume that this announce course method can also go wrong. Well, this is the restaurant that we're in right now. We're sitting down and we want a nice 3-course meal. And before we start to order, the waiters come up to us and tell us what the daily specials are, right? The starter today is this, the main course is this, the dessert is this. What if I'm really into starter courses, right? But some ingredient is out of stock, and the waiter comes up to us and says, sorry, there are no starters today, but would you like a main course? Well, in that case, for our example, I want to say, no, I don't want anything at all. Let's leave and find another restaurant. What are you people doing here? Right? That is, so bear with me here, right? Probably you would just take another course, but in this example, we're standing up and leaving because we don't like this place. Okay, so announce course method can throw an exception, and I've, in the example code that is also available to you to download afterwards, I've called this an out of stock exception, if something is out of stock. For example, what if it takes a long time to announce the main course here on line 10, but in the meantime, announcing the starter course fails because of an out of stock exception. Well, then the entire menu, announce menu method that we see here is going to wait for main.get because it takes a long time. But by this time, we already know that starter.get is going to throw an exception. So that's kind of unfortunate because we're waiting for a result that we already know is not going to help us. We will never be able to construct a valid multi-course meal here, because one of the gets is going to fail. So that is not ideal. And there are more ways in which this code can go wrong and run in a way that we don't want it to. For example, if an exception happens here in the announcement of the main course, then of course it will be thrown by line 13, main.get, right? But announce course starter on line 9 in the separate thread in the executor service will continue to run even after the entire menu has failed, because a new thread was spawned here, and we cannot be sure that that thread is already done with its work. And overall, what if the thread that is running this code, let's assume it's the main thread, for example, is interrupted? Then this interruption will not propagate to the subtasks, right? All the subtasks could happily continue doing their work, whereas the method that started them is already been interrupted. So that's also quite unfortunate. So ultimately, the problem here is that our program has kind of a logical structure. There are tasks and subtasks, and we want to announce mains and starters and desserts before we are done with our work. But these relationships, they exist in our minds, right? But we cannot express them in the concurrent code as of this example. So pros and cons again, the task can directly return a value now with executor service, and we have separated workload and run mechanism. We could run it on 6 threads if we wanted to with just one single change in the code. But executor service always waits for all tasks to terminate, even if it has failed, right? And it also allows unrestricted patterns of concurrency. So what do I mean by that? Well, what I mean is executor service, it doesn't enforce any task structure. So you could create an executor service, and then a second thread that is running could submit work to it, and the threads that actually execute the work, which are modeled inside of the executor service, would have no relationship to either the first or the second thread. And to illustrate that, I want to give an example. So who has, some point in their life, created a program in the classic programming language BASIC or QBasic? Yeah. Okay, well, this example will speak to you then the most, because spawning a thread in an executor service is like the go-to statement in BASIC, right? You can compare those because you are doing a one-way jump. You're saying go to 040 and then it will continue at 040, but you have no idea where it will go next. There could be other go-tos under the line 040. So if you have a go to 040 on line 100, for example, you're not sure that it will ever return there. It's a one-way jump. Spawning threads from an executor service, they are like one-way jumps. That means that we cannot be sure that they'll eventually return to a certain point in the code. So we have no way of knowing what is started up and where it's going and when it is terminated. So we will remember this drawback when we get to structured concurrency. And then I also want to talk a bit about thread locals. So thread locals have been in the Java language since Java 1.2, and a thread local is a very unique way of creating a variable that is unique to its own thread. That means that if you create a thread local variable, there will be an own independently initialized copy of the variable for each thread that comes across that code. So many application frameworks use thread locals in a way to identify, for example, certain requests or certain user sessions. So a request ID would be a very good example to generate with a thread local, because each thread that uses the request ID will have a different value. Which it's a cool construct, right? Most of the times we obviously want a variable in different threads to be exactly the same to avoid concurrency problems, right? But in this case, we actually want them to be different. Okay, well, as you have noticed in my example code is about courses and announcing them by waiters. So let's create an announcement ID then and have it be unique for every announcement that we make. Well, then we could create an announcement ID class like this one, get the thread local, and each time this code is accessed, well, the first thread that accesses this code will get the value 1, and then the next thread that accesses it will get the value 2, and the value 3, and so on. So that's how that works. Well, in that case, if we have exposed this thread local, then we could just use it right here, announcement ID.get, and use it in some kind of a logging line. Today's starter course will be, for example, this course, and there will be announcement ID that is logged along the way. And in a different class, we can use the same instruction again, and it will return the same value when the same thread runs the code. Pros and cons again. Thread locals are a very good way to avoid cluttering method signatures. When you want to pass this value along to all your methods, you can just put it in thread local and make it accessible to more classes. And it's a very elegant way to bind data that is unique to the current thread. So if that's your use case, thread local used to be a very good way to go. But there are also drawbacks, because thread locals are always mutable. So all the code that has access to the get method of the thread local can also set the thread local again. So that's kind of a security risk. Also, they have unbounded lifetimes, and what I mean by that is they live as long as the thread lives. So if you've got short threads, the risk is minor here. But if you are using thread pools, for example, which a lot of people did and probably still do, if they haven't switched to virtual threads yet, well then, these thread locals could be in memory for a very long time. And also, if the created threads spawn child threads again, then it can be memory intensive because the thread local values have to be copied to the child thread. There's no way for classic threads to refer to the parent thread memory location. So you're having some redundant storage there of thread locals. So those are the drawbacks. And of course, we'll get into this when we talk about the new features. By this point in the talk, you're probably wondering, why does this stuff interest you? I mean, it's quite low level, and it's, do you deal with this on a daily basis? Well, no, right? But I do teach a course at InfoSupport and also for a few of my clients about concurrency. And when I teach that course, I always tell people that follow it, you probably won't need this tomorrow and probably also not next week. But when you've got a race condition on your hands in like 4 months or 5th month, you will be the one who knows how to solve it. And that's kind of a good feeling, right? So that's the reason why I like talking about the subject. And we do have this course also available to you, by the way. So if you want to learn more after this, please check out this link and you'll be in contact with me and my colleagues. You can learn more than follow a 2-day course. But also I like to write blog posts about new features in Java. So I've written a few in the past. And I noticed in the past Java versions that a lot of stuff was being done that had to do with concurrency, of course, because virtual threads were introduced in Java 21. But also after that, a lot of interesting things happened. And I came across them, updated the course, and got the idea for the talk. Right, and that's in general what I like to do. So at InfoSupport, I'm a trainer and a technology advocate. That means I get to spend my time teaching people about Java, about application frameworks. I get time to blog about Java and open source, be here at software conferences. So that's something that I really like to do. If you want to keep in touch, my handle is Hannotify almost everywhere. So find me and keep in touch. I always appreciate that. Then it's time to jump to virtual threads, to get to the newer stuff, the more modern stuff of Java, right? And I think in the stations analogy, our current station, the virtual threads, because in Java 21 it was made final, so that means that we can safely use it in production without the risk of it ever changing again. Any changes will be backwards compatible, of course. So virtual thread is a lightweight thread implementation with no explicit mapping to an operating system thread. Classic threads do have that limitation. Every thread you create in Java immediately creates a thread in the operating system. This is not the case with virtual threads. And because this mapping is not there, it is also very lightweight in terms of memory usage, which also means that you can just create them and dispose of them at will, right? So it's very cheap to create them, cheap to dispose of them, and this is a big difference with classic threads. And they are scheduled by the JVM to run on a carrier thread. So we have to introduce some new terms here because everything I called thread until now, we now call a classic thread, a platform thread, or like we said here, a carrier thread, as opposed to virtual thread, which is the lightweight variety here. And I've brought a graphic here with me to make this a bit more clear. At least the graphic helped me to understand. Right, so these are the threads that run in your operating system, right? The green circles. And the blue circles are the threads that you can still create with Java if you do a new thread. We now call them platform threads, which means those threads can be created by Java and they will have this one-on-one mapping with operating system threads. But if you create a virtual thread, this mapping is gone. You can create multiple virtual threads and you don't have to specify on what platform thread or OS thread these are going to run. So the JVM scheduler will figure this out for you. Actually, it would be very plausible because typically the tasks that are run by virtual threads are small, that they could run on the same platform thread. I don't know what the JVM scheduler here does. I know it keeps a few old school classic platform threads in memory, and they are available to virtual threads as carrier threads. So it could be that this task over here runs on this blue carrier thread, then terminates, but this one is still kept in memory, and then the second one has to start and gets picked to run on the same carrier thread as the one before. Or not. I mean, the whole point is that it isn't our concern anymore. We don't need to have control over what platform thread is being used. Actually, virtual threads are kind of like virtual memory. An operating system, as you may know, maps a large virtual address space to a limited amount of physical memory. And similarly, to simulate a lot of threads, in Java, the Java runtime maps a large number of virtual threads to a small number of operating system threads. I always compare them in the course to trains. So classic or platform threads, they are expensive to create and quite slow to get started, and also quite slow to stop again, like a heavily loaded passenger train. And I'm not the only one who thinks this is a good analogy. People before me, far smarter and greater than me, think the same. And if we continue this analogy, then if a classic thread is a train, then surely a virtual thread must be a taxi, right? Fast to stop, fast to start, carries a small load, but can get you there fast. Well, not in this traffic jam, but you see my point, I think. By the way, I couldn't find a picture with 100 New York taxis, so I generated this one using AI. Some of the taxis are split in half or facing the other way. A few of you noticed. Yeah. Well done, good work. I have to get by. Okay, so let's see how virtual threads speed up stuff, because they can speed up stuff just in very specific situations. So for this example, we're doing some stuff on a platform thread. And with platform threads, they are expensive, so we probably pull them from a thread pool right here. And then the green block tells you we're doing some work, and afterwards we're fetching from some database data. Obviously, we have to wait, so this thread is blocked until the database responds. And again, with an external service, we block. Then we send some data to a service, block again until we get a 200 OK from the service. We can release the thread again to the pool. So there are 3 periods of time where this thread is not able to perform any more work, and it is blocked. If we would translate this to virtual threads, this is what would happen. The left vertical line is exactly the same, but because this runs on a virtual thread, the blocking periods have a different effect. Yes, the virtual thread is blocked here, but the virtual thread is a concept that only exists within the JVM, right? So that means that this blockage is not translated to the OS threads. Actually, the OS thread, the carrier thread, just performs the green stuff and then it's done and is free for other work. And imagine this green block runs on a second carrier thread. Well, then that thread is busy for that period of time. But overall, all these blocking periods, they don't get translated to the carrier thread here. The time that the first thread was blocked is now available to be used by other virtual threads. And because virtual threads can be mapped to any other operating system thread, that space is now available to use. So no, your work will not be processed faster than before, but it can offer you higher throughput. There's more work that can be done in the same amount of time because these carrier threads can be used more efficiently. I was at a talk on DevOps last month by Gregor Hope about architecture and about throughput. He had a good quote that I wanted to include: wider bridges, not faster cars. Right? So virtual threads don't let you go faster like a faster car, but it offers a wider bridge, so more cars can get to the other side at the same time. So that's a good analogy, I think. What would we have to do if we wanted to do our course announcements with virtual threads? Well, for executor service, that is a very simple answer. Did you see that? We just use a new factory method that makes sure that virtual threads are used. And you probably noticed that there's no option anymore to define how many threads you use, and that is deliberate, right? Short tasks are meant to be done by a single virtual thread only, and a lot of them can be created. So if we submit 2,000 announced course invocations here, 2,000 virtual threads will be created because it's so cheap to create them and dispose of them. So what are the limits here? Well, millions of threads can run. I have a demo on my MacBook Pro M1 during the course where I almost get to 1 million virtual threads, but probably you could do more if you wanted. This means that we can use a thread per request instead of this thread sharing that we used to do with thread pools for years. Creating them and disposing of them is cheap and fast, and we already saw we can achieve higher throughput. But it's not suitable for long-running CPU-intensive workloads. I mean, you could try, but of course, because there's this scheduling mechanism, you're losing some time over that. So if you already know that you've got a lot of CPU-intensive stuff, that will probably run faster on classic threads because you don't have this, this overhead of scheduling. And lastly, pin threads. Oh, this is not lastly, I have another item, but pin threads are an issue because when a virtual thread is inside a synchronized block or method, it cannot be unscheduled at that point. It has to stay pinned to the carrier thread for the duration of the synchronized block. Or when you execute a native method or foreign function that is outside of the scope of the JVM. And finally, thread locals do not perform well with many threads. I already explained to you what the risk is here. Now, if we got millions of threads that also spawn millions of threads, this memory problem might be an issue in the future. So that means that we've listed all our drawbacks, and the question I want to ask myself now is what drawbacks are amplified now that virtual threads are available? In my opinion, it is this one, unrestricted pattern of concurrency, because there are more threads available to us, so these patterns will become more complicated. And like we just saw, the memory intensity of thread locals. Of course, this question is rhetorical. It's never the final station. More features are being developed that exactly want to focus on the drawbacks that I just mentioned. So let's get into structured concurrency. This feature is in third preview in Java 23 and expected to be in a fourth preview stage in 24. That hasn't been announced yet officially, but I expect it to be. The preview version features always has this little asterisk next to them, right? You can use them, but they might change, and you also have to pass the compiler option enable preview to be able to try them out. So keep that in mind. What problem are we trying to solve, and how can structured concurrency help? Well, this is the problem we were trying to solve. In this piece of code, all kinds of exceptions could happen, but there was no way to cancel the stuff that is still running or to avoid starting it even. But what if we would consider a single-threaded version, right, of the same code? So the waiter on call today is Elmo. The poor thing has to do everything by himself. But a lot of the problems that we saw earlier kind of disappear if you do a single-threaded version, because what if the announcement of the starter course fails? Well, then an exception is thrown. The other work, of course, is cancelled because the exception is being thrown here. So because it's a single-threaded version, of course, it's a lot simpler. But I want to have some of the properties here and translate them to the concurrent example. So that's our approach and what we expect from structured concurrency. It can preserve the natural relationship between tasks and subtasks. And this is kind of how it works. When you consider the executor service version of our code, it's more like the image on the left, where we spawn off a thread, this one-way jump. We have no idea if it will ever return. But with structured concurrency, we define a specific scope in which subtasks can be spawned off, but they also have to complete within the scope. And only after the scope has been shut down, then we will be sure that all tasks are finished. And this is a very simple example, but you can build all kinds of hierarchies with your subtasks just to, you know, use the logic that is in your head or in your domain, and what the best way is to divide the work, so you can use this to your benefit by creating a good hierarchy here. So, like I said, structured concurrency comes with scopes, and a scope continues until all child threads have completed, with the results that your lifetime operations are strictly nested, and also means you get a streamlined error and cancellation propagation, which also leads to more reliability and observability in concurrent code. So to summarize, if a task splits into concurrent subtasks, then they will all return to the same place, which is the code block of the task. Okay, so time to see that in action. Don't you agree? Okay, so I've got a piece of code here. It's just a simple main method. I could have written this shorter from Java 23, of course. I'll do that next time. And right now, the code is using the single waiter restaurant code, right? So poor Elmo is very busy announcing all these courses. This is the stuff he says to his customers. I'll wait your table today. Today's starter is creamy tomato soup. Today's main is ratatouille. Today's dessert is apple pie. And all these indented lines is Elmo talking to his colleagues, asking the chef, please pick a starter course, please pick a main course and a dessert course. But now, of course, we are going to create a structured concurrency version of this. Let's create a structured concurrency restaurant here. Create a class. It will implement the restaurant interface, which also means I have to implement this method here. And let's introduce a few waiters. 3 favorite Sesame Street characters, right? Now, when we start off structured concurrency, we start a try with resources statement, so the scope will be automatically closed after this. And we use the class structured task scope, and in this case, shut down on failure. I have done Kotlin all week, as you can see. At least I didn't forget the semicolons, but still. If we want to announce courses, this is what we do. We call the fork method on scope. This will start a new thread, and structured concurrency uses virtual threads by default, right? It will run this in a new virtual thread, and this also. Now we have forked the tasks. Now we tell the scope to join, means wait for everything to finish, and we also tell it to throw any exception if it fails. What this means is, by the time we have executed this piece of code and we get to line 23, we can be sure that no exceptions have occurred and we are dealing with valid, successful results here. Well, that's very good. That means we can just return a null multi-course meal, like we saw on the slides before, and call get on all of these subtasks. Mind you, we are not working with futures here. This is a new, actually a new return type called subtask. And right, sealed interface subtask. And when I get to here in this piece of the code, it will not be a blocking call, right? This will be the blocking call. And after we get to here, there's no blocking anymore. All these results will be available. So let's run this code and see what happens now. Of course, we will have 3 waiters now. And there are multiple things different than last time. We have 3 waiters. Also, you see these announcement IDs where I talked about. There are 1, 2, and 3 because we are using thread locals here. And what we also see is that all courses have been announced successfully and they arrive out of order. But of course, that's concurrency for you, right? But if I repeat this a few times, something like this will happen, right? So every ingredient has a 5% chance of being out of stock. In this case, it is probably zucchini. We are completely out of zucchini, so we cannot serve ratatouille today. Well, we picked tomato soup, dame blanche, and ratatouille, but as you can see, no course is being announced whatsoever, right? Not even the creamy tomato soup. So probably the exception occurred before the announcement of the tomato soup could have been done. And because of this shutdown on failure, the entire scope is shut down and nothing here is announced. And the people in the restaurant will probably get up and leave, right? And find a better place to have their dinner. So that's the effect of the shutdown on failure. Scope. Right, so this is the accepting code that we just created in the live demo. So this pattern shuts down the scope when the first subtask fails, and this pattern is also called invoke all. This demo I'm going to skip, but it's a different version of structured concurrency where we're not shutting down on failure, but where we're shutting down on success. And this is exactly the solution for the story I told at the start of this talk. The waiter is listing all these drinks, but you already know after the first or the second one which one you want. So this code emulates that, right? We get a guest in the parameter here, and the guest has a kind of drink preference, and the waiters, Zoe and Elmo, are listing drinks in certain categories, right? And once one of these get drink orders returns a result which is of type, where it is drink order, then the scope will shut down. So for example, if one of my preferences is, I don't know, espresso, and Elmo lists espresso, then it will be a successful result, and the rest of the work will shut down, and you will see that he will not even announce the teas, the cocktails, and the distilled drinks. So this is another strategy to use structured concurrency. Shut down the scope, return the result when the first subtask succeeds instead of fails. This pattern is also called invoke any. And if you would want, you could create your own shutdown policies by extending the class structured task scope if you want. For example, gather all successful things, or gather all failures but still continue, or some other thing that you need. You can do this by implementing the handle complete method. Okay, so we've come to a section I like to call sanity checks. It's one of my favorite sections, right? It contains a few questions that you might have already. Wait a minute. Executor service allowed us to pass a thread configuration, right? 6 threads, 3 threads, cached threads. How do I get this to work with structured concurrency? Well, the answer here is the best way to do this is virtual threads. That is why it uses virtual threads by default, but you can use this structured task scope constructor and pass it a platform thread factory to have it use platform factories if you want instead. So that is what you can do. Okay, why do we need all these new scope classes then? Why couldn't they just enhance the executor service interface? Well, that is because of backwards compatibility. Executor service is meant to do unrestricted concurrency, and it would be very hard to get that back to a structured way of doing things. So that is why they introduce a new API. However, if you've got code that uses executor service that is structured by nature, I think it's very easy to translate this into structured concurrency. I don't expect you to have any problems with that at all. Final question. You called this patterns invoke all, and I know executor service also has a method called invoke all, so why do we still need structured concurrency? Well, this is a good question, and it is true that these patterns are supported by executor service also, but there are also differences. So cancellation doesn't work with executor services, right? They can only wait until all tasks have finished, whether exceptionally or successfully. And it's also not possible to create a hierarchy of tasks, limit the scope, or make the task return to the same place, limiting resource leaks in the process. And of course, custom shutdown policies are not possible with executor service. And virtual threads by default, in executor service you can configure this, but it's not the default, right? Okay, I've created a slide that lists all the differences between executor service, CompletableFutures, and structured concurrency. In longer talks, I'll go through them. I don't have the time today, but if you're very interested in the differences between these three, you can take pictures now. It is a good overview, right? When to use what benefits to the first, what benefits to the other one. And the link below is also a very good reading tip if you're into this. I'll give you people a bit more time to do that. Very good. By the way, the slides can be viewed on my website later, so if you missed this slide, no worries. To summarize, virtual threads help us deliver an abundance of threads. We can use a lot more threads at the same time, and that also means that they have to be coordinated correctly and robustly, and that is where structured concurrency comes in for us. Okay, then we have to talk about scoped values, another station in the future of Java, or one that is actually being worked on. Today, this feature is being progressed together with structured concurrency, and they've all had the same previous statuses until now. So they work in conjunction with each other, right? Third preview in Java 24. What problem are we trying to solve with scoped values? Well, it has to do with thread locals. Like I said, they are good for multiple things we already talked about, but they are always mutable, have an unbounded lifetime as long as the thread lives, and are memory intensive. Well, scoped values aim to fix these drawbacks. They are values unique to a thread that may be safely and efficiently shared to methods without using method parameters here. And they are immutable, so you can write them once and then read them multiple times, but you cannot overwrite them from external code. They have a limited lifetime, which is made visible from the syntactic structure of the code. So the braces blocks that you use with scoped values also indicate how long this scope value is available. So that is a little bit more comprehensible. And it is robust because data shared by a caller can only be retrieved by the legitimate callees and not any other part of code outside of the scope. And this is what they look like. It's just a scope value type with a generic type argument, in this case string. And to use it, you create an instance called new instance here, and then you create a scoped value.where, you refer to the value itself, then you bind the value hello, and after that you run a method. In this case, it's called run because you pass a runnable. It can also be called call when you pass a callable. And everything that's in this run method here is within the scope of the scoped value. So that also means that the bar method can access x.get will print hello. But if you do x.get outside of, for example, the first line of the foo method could be x.get, we'll throw an exception because the scoped value is not in scope. We don't have time for this demo, but I can show you what the end result would look like. So if we would use scoped values in announcement ID, this is what it would look like. And code is kind of the same. The call side is where things are a bit different. So if we want this announcement here to work, announcement number X, right, we can delegate that to announcement ID .get, which will again use this atomic integer here, so it will be 1, 2, or 3, will work exactly the same, and the scoped value is scoped here. Scoped value.where, announcement ID.scoped value, bind it to next ID, and make sure that next ID is available to everything in the call method. In this case, it is the entire announce method. And as you can see, the announce method calls a chef method first. So that also means that in the chef method here, we can also do announcement ID.get, and it will have the same result as before. If we would do it outside of the defined scope, we would get an exception. So scoped values cannot be mutated, but they can be rebound, right? So in this example here again, we have the scoped value X. We've bound hello for the scope of the bar method. So in the entire bar method, the result will actually be hello, unless we rebind it. So at line 9, we rebind it here to say goodbye. So we're actually created a little nested scope here. And the nested scope is, in this case, a lambda that calls the bus method, which means that in the bus method, x.get will print goodbye. So it's like a nested thing. But after the bus method completes, well, then the scope for the scoped value is also complete, and x.get will print hello again. So they can be overwritten, but not changed, right? Hello can never be changed here. It will remain hello. And this is one of my favorite features because scoped values and structured concurrency work together here. If you want to inherit scoped values, you can, right? So if you combine a scoped value like here, drink order ID, we set it to 1, then for the entire call method, or for the entire lambda inside the call here, 1 is available when you refer to drink order ID. But also, these threads that are forked here, by means of structured concurrency, the value is propagated, inherited. And the reason why this works is because with structured concurrency, we can be sure that these threads, they terminate within the scope. So we're sure that they're not spawning off new threads that are outside of the scope. When we get to line 15, scope join result, the scope has been terminated, and we can be sure that the scoped value that is passed here is not shared elsewhere. So this is a very unique feature of the combination of scoped values and structured concurrency, how they can work together. Okay, so what if you say right now, I have thread locals in my source code, should I migrate? And are they always a better solution? Well, this is my opinion on the matter. You should migrate when you have thread locals that deal with one-way transmission of unchanging data. So that means your data is set once, it is not changed from outside, and you only use it to read from other places, right? Because so to summarize, you use it in an immutable way. Well, then scoped values are a very good solution. And of course, if you expect to use many virtual threads because the risks are amplified with more threads, I don't think you should migrate when your thread local is used in a two-way fashion. It is being set. Well, scoped values don't support that, so it's not feasible to migrate. And also, you might want to hold off on migrating when you don't expect to use virtual threads at all, because the risks are diminished when you don't use that many threads. So, of course, you can make up your own mind, but here are my thoughts. Summarizing, thread locals, they didn't limit mutability, and they perform badly with many threads, and scoped values support immutable values, are strictly defined when it comes to lifetime, and they can be inherited efficiently. So what does this mean in practice? Right, that's all cool theory. How is my work going to change? That depends, of course, on the role you're currently fulfilling. So if you're like a developer advocate or trainer, like me, you would probably have already started using them and talked about them, because nothing can stop you, right? Just be on the bleeding edge, and when it fails, your students will have a good time. If you're working on a framework or a library, well, then please start using these features because they are in preview status for a reason. The people working on Java want some feedback here to see if the features worked as they intended. But keep in mind that virtual threads is currently the only feature that is finalized, so the other ones can still change. If you're a Spring developer, this is the way you could create a simple task executor bean to use virtual threads by default. Spring 6.1, probably the newest Spring Boot version also. So that's the way you could use virtual threads. If you work with Jakarta EE, you would probably use managed executor services already with resource annotations. And if you would want to change that to virtual, then this is a very important property virtual it's true, and you change the annotation to managed executor definition. And Jakarta EE also supports structured concurrency already with managed thread factory. Here we use this overloaded structured task scope constructor with a specific thread factory that is managed by the Jakarta EE container. And if you like Quarkus or do a Quarkus project, there's a run on virtual thread annotation that makes sure an annotated method runs on a virtual thread. So that is what we can do. Wrapping up, have we come to journey's end? Obviously, the answer is no. But in the near future, a lot of changes to the API are happening, actually. So I want to quickly go through that. I'm skipping these ones because these are not very near future, but this is confirmed future features. I said virtual threads have a problem with pinning. This is going to be solved in JEP 4.9.1. I just saw it targeted to JDK 24. So that means that this drawback will no longer be an issue. They'll change the language and allowing virtual threads to acquire, hold, and release object monitors. That is essentially the solution. Doesn't matter who carries it. And the structured concurrency API will be evolved a bit. This JEP is still in draft, but I expect it to get an official JEP number in the near future. And these are changes to the API that came from feedback, right? Feedback from people that use it. So this is the API that it is right now with the new invocation right here, and they are going to change it probably in Java 24 to this. Right, that went a bit fast. This will become this. So two major changes. This constructor invocation is no longer necessary. It will work with a factory method, and they will call it open. You're opening a scope of structured concurrency, and the default behavior here will be shut down on failure if you don't pass anything to open. And the feedback was also, why do we have to include throw if failed? I want that to do it automatically. So in the new version of the API, join will throw the exceptions automatically. You don't have to, because you might forget to do throw if failed, right? No need to opt in here. And this open method expects a parameter. There's an overload that is a joiner type, and you see this here in action with the shutdown on success example. This is how it looks in Java 21. This is how it probably will look in Java 24. So the same open method, but we pass a joiner here that returns a drink order, and the joiner is called any successful result or throw. That means that all kinds of behaviors for the structured concurrency scope can be implemented as a joiner, and you can write your own custom joiner from Java 24 and onwards. And there's also an overload that takes thread factories, like you see here, or timeouts. This is called a configuration function, so the API changed a bit, but the same things are still possible. And became a bit more extensible. And also, the API will provide a few custom joiners. So not only any successful or throw, but all successful or throw, await all successful or throw, or all until. So a lot of new options to play around with and use with your concurrency issues. Or hopefully you don't have them, right? And like before, you could create your own structured task scope strategy. In this case, you can create your own joiner starting from Java 24 and build the behavior that you want there. So I think we are almost out of time. So if you still have any questions about anything I told you, see me after the talk or reach out to me online. I'm happy to talk about this subject. It's really dear to my heart, so I'm always up for that. If you want to read more, I'll leave the slide up for a bit. I have the slides on my website. You can just click through them with the arrow keys. And the code example is on GitHub if you want to try out the code that I wrote and see it for yourself or extend it if you want. That's all fine with me. And with very quick question then, yeah.
Yeah, so this is all quite advanced, let's say that way. We normally not use this. In case of, for example, streams with parallel streams,
Yeah.
does that automatically out of the box can use virtual threads?
Yeah, so your question is, using parallel streams, how do you make that, can that be used with virtual threads?
Yeah.
I think the answer is no, because the default thread pool that runs for parallel streams is the ForkJoinPool. And ForkJoinPool, by default, runs with platform threads. However, you could, of course, create a custom ForkJoinPool with virtual threads if you would want, but it's not supported out of the box. So by default, it will still use the ForkJoinPool. Yeah? Okay, thanks for the question. Like I said, if you have any more, reach out to me. Thank you for your attention today and enjoy your conference.